Yeah, I'm going to talk about recent advances in MVCC, but when I started sort of researching on the topic, I realized that I can't just talk about recent advances. I'll have to give some context of, why, there was a need for improvements in the way MVCC is handled in Postgres. So I'm going to do that as well. But just to introduce myself, I'm one of the organizers of the event and a regular speaker at this conference. And I've been contributing to Postgres for last 15 years now in various capacity. So that's the agenda for this talk. I'm going to talk about, start with basics of transactions and then how MVCC is used to, support various characteristics of transactions in Postgres. What are the challenges posed by the MVCC implementation in Postgres, and then how we are trying to mitigate those challenges over the last few years, and what are we going to do in future. Obviously, MVCC talk cannot sort of be complete without telling you about how vacuum works. I'll go into that briefly as well. So let's start. I mean, what are transactions? I mean, I don't think I need to explain that in great detail here. You are all from the database background, and the first thing that we learn about databases is transactions. So it's an atomic piece of work. It's a logical unit of work that application wants to execute in a database. The work that is done by any given transaction must be atomic, it should be consistent, it should be isolated, and it should be durable. I mean, those are the ACID properties that we always hear about in context of transactions. In Postgres specifically, each transaction is assigned a 32-bit. It's a 32-bit integer, and it's sort of important to know that in context of MVCC, and that's the reason why I mentioned that. So when Postgres started, maybe 2 decades back, or even till say 10 years back, 32-bit integer seemed to be like a large enough value. If you are doing 10 transactions per second, it will take you 7 years to sort of reach the limit of how many transactions you can represent in a 32-bit integer. But these days we know that we know customers who are doing thousands of transactions per second, in which case it can take as little as 24 days to before you run out of your transaction ID limits. So the reason why I gave you that context is because we are going to refer to transaction IDs quite often while understanding how MVCC works. So it was sort of important to know. So MVCC, or multi-version concurrency control, that's the the full form of the word. It is used by Postgres quite heavily. Out of the 4 major properties that we talked about that any transaction should basically support, I would say atomicity and isolation are the 2 properties which relate more heavily to MVCC. So in a multi-version concurrency control system, what we do is whenever you do update on a row, you create another version of the row. So I mean, the basic or the most trivial operation could have been, you allow only one person to update that row and somehow basically just deal with one version. But that's not how Postgres works. So instead what we do is whenever you do update, you create another version of the row, and somehow now you have to manage these 2 versions of rows. And imagine if you are doing repeated updates to a column or a row, sooner or later in your database you might end up having multiple versions of the row, and then you need all the I would say mechanism to sort of handle that situation. So even if even if I'm saying, when you update a row, you end up having multiple rows multiple versions of a row. Any given query at any given point can see only one version of the row, and we have to somehow guarantee that in a database. Otherwise, imagine your application is updating a row and another transaction is selecting from that table. If you start seeing the same row twice because there are multiple versions of the row in the table, there would be chaos. So the database has to guarantee that even if internally, no matter how many versions of the row are there, any query should at any given point should see only one version of the row. I would say at most one version of the row. Obviously, there are situations where you may not even see that version because it's deleted for you. And so in order to achieve that, what we do in Postgres is we stamp each version of row with 2 transaction identifiers. And these are 32-bit integers, as I said. So you stamp the creating XID, and you stamp a row with the destroying XID. And then there is something called as MVCC Snapshot that we use to then, sort of, while you are reading the table, you use the MVCC Snapshot along with the information that is stored in each of the rows to decide whether you can see a particular version of a row or not. And we are going to get into details of how we do that. So here is an update example, pretty simple example. You start a transaction, you update some table and change some column in that table. The problem is, after you run your update, you may decide to either commit the transaction or abort the transaction. And sometimes it might happen because your connection breaks with the server or the server goes down. So even if you want to commit the transaction, it might eventually lead to an abort. And the database must be prepared to handle all these eventualities. You can't say, because my connection dropped, even though I wanted to commit this particular update, it got aborted. I mean, the database has to guarantee, its asset properties, its consistency, irrespective of what happens to the transactions. So there are 2 ways you can sort of address this problem, because as I said, when you start a transaction, run the update query, it can either abort or it can commit. And if it commits, you want to make sure that whatever change that the transaction has made, it remains durable on the database. Whereas if it aborts, you want to make sure that whatever change the transaction has made is sort of wiped out from the database and should not be visible to anyone. So broadly, there are 2 ways you can do this. Either you can update the existing data in place, so you overwrite your existing row with a new row, and you move your existing row to some something else. I mean, Oracle, for example, you have undo segments where you can copy the current row, whereas change the existing row in place. In Postgres, what we do is the updated row is created as a new version. So your existing row stays where it was, but a new row is inserted with the new value. To get into slightly more details about how exactly it happens at the I would say at the internal level, is that the 2 XIDs that I have marked there, XID1 and XID2, in the old version of the row, we call them xmin and xmax. Xmin being the transaction which is creating that particular version of the row, and xmax being the transaction which is sort of deleting that row or expiring that version of the row. So in this case, the original row that was there in the table, it was inserted by a transaction with identifier XID1, and let's say it was eventually expired by another transaction with XID2. Whereas the newer version of that row was inserted by XID2 and it hasn't been expired by anything. I mean, it's the latest version of the row. And this is an update example, right? So you got your old version and you got your new version linked through a sort of through a chain, and that is something which is again internal to Postgres, and that's how we sort of identify the versions of the row. So I mean, these are sort of important terminologies when you, I mean, some of you probably would already know, but typically these are the system attributes of any row on a Postgres. So you can actually do select xmin, xmax, star from my table, and it's going to return you not only your data, but xmin and xmax, which are the creating and destroying transaction of that row. So I'm trying to basically explain that through graphics. So if you recall, in our original update example, there were two eventual possibilities. One was either the update would commit or the update would abort. Now, if the update commits, what happens is your old row becomes sort of dead, or it will become dead at some point, because once sufficient time has passed, nobody is going to be interested in that data that you updated, say, 24 hours back or 3 days back. What they would be interested in the new version of the data, and that's the new row, and that's why I'm showing them the colors. I mean, red is sort of it's expired, and green is the live version of that row. So this is the the normal commit case, and this is how your database would look like at the end of a committed update operation. Whereas if you look at the aborted update operation, it's going to be the other way around, because if your update aborted, and even though you basically database created a new version of the row, because when the update happened, it didn't know whether it's going to commit or abort. So it had created a new version of that update, but if that update aborts, then your new version of the row has become pretty much dead. I mean, one, nobody should have seen it while the update was happening, and because the transaction aborted, nobody should ever see it again. So the new version of the row becomes dead, whereas your old version should stay intact. So even if you had, or the database had stamped the old version with XID1 and XID2 and the new version with XID2, we have to have sufficient intelligence in the database to sort of decide whether out of these two rows, which row should be visible to a given transaction. And as I said, at any given point of time, you can't have more than one version visible to any transaction. And here, transaction, I'm sort of using in a loose way. A more appropriate term would be MVCC snapshot, because a transaction can run with different snapshots, and even for a given transaction, at different points of time, you can see different versions of a row. And this is the case, and again, I'm not going into isolation levels, etc., but that's the default behavior with read committed transactions, where you always want to read the most recently committed data, and not even if in the past the same transaction had not seen that row. This is a insert example. Again, all DMLs, inserts, deletes, update, everything make use of MVCC to provide transactional guarantees. And in an insert case, and I'm taking two different cases of insert, one where insert finally committed and the other case where insert finally aborted, a new version was created in the database. Now, if the insert finally committed, then you want that row to be visible to everyone eventually, if not immediately, eventually. Whereas if the insert was aborted, that row version should not be seen by anyone at any time. And the way the Postgres database sort of implements that internally is by using MVCC and MVCC snapshots, and sort of correlating with what's there in the rows with your snapshot. A converse example is obviously the delete example, where if the delete is committed, you want that row to sort of vanish from the database, whereas if it aborted, then that delete action should not be sort of made permanent. So with that context, I want to sort of talk about how data is read using MVCC snapshots. Now, we saw how the rows are stamped with creating and destroying XID, but what makes them usable is what we call MVCC snapshot. And a snapshot is nothing but my view of the database at this point of time. So if I'm taking a snapshot from the database, I'm saying, I can see all effects of these transactions because they had completed before I started. They had sort of committed before I started. I can't see effects of these transactions because either they haven't yet started or they started after I began my scan. And then there could be in between, right? I mean, there are some transactions which, that's how we internally represent it in snapshot. But at a very high level, that's what it is. I want to know what is visible to me and what is not. And to do that, we use a snapshot. And what snapshot typically contains is it tells me in a efficient manner, because obviously, as you imagine, there are, if 2 power 32 or 4 billion transactions out there, you can't practically say that, these 10 transactions, these 100 transactions are visible to me and these are not. So there is a sort of a very optimized way of representing that. So I say anything before this XID is visible to me, anything after this XID is not visible to me, and between this range, which you would imagine is the range of current transactions running in the system, I would say these 10 are still running, these hundreds have already finished. With this information, and then looking at what's stored in the row versions or row headers, we can exactly determine which version should be visible to a given snapshot. So I'm just trying to in pictures, just trying to explain how your database state might look like after some number of insert, update, deletes operation. So the dark red blocks in this diagram are tuples or are rows which nobody should see, not now, not in future, because they are deleted, they are gone. Either they were inserts which were aborted or they were updates which were finally committed, and sufficient time has passed when that action was done. Those row versions are still there in your database, but they should not be visible to anyone. The green boxes, on the other hand, are the rows which should be visible to everyone. I mean, they were inserted long back, say, and everyone should be able to see them. The light red boxes are sort of border case. In a sense, they were deleted, but there might be still queries running in your database which are able to see them, because those queries were started before the actual delete operation took place. So even though the transactions which deleted those rows have committed, which means those light red boxes at some point would turn into red boxes, dark red boxes. At this given point, there might be queries in your database which can still read those. And that's why it's important for Postgres to maintain different row versions at different points in time. You can't basically just say, I'll have at max 2 versions of a row. There can be 100 versions of a row. Eventually there would be one, but in transient time there can be many more versions. So typically when a scan happens in a table, you go block by block. Obviously I'm taking simplistic example. If you got an index, you'll hit via index. But if you are scanning this table, you'll check every tuple in the table, see if this tuple is visible to so tuple and row are sort of, I can use interchangeably. But I will say if this row is visible to me, if yes, then return it to the the application or the query. If it is not, then move on to the next version of the row. Next version of the row or next row in the table. So, what are the challenges? This is a great thing. maybe I should just spend like a minute on talking about why MVCC is useful. I mean, you might say, we are creating multiple versions of the row, and then this is going to lead to challenges that I'm going to describe. But the great thing about MVCC is that, it provides, you can build a greatly concurrent system with that, because updates are creating new versions. The reads, they don't block on update, because every read, even if it has to read a different version of the row, it can work without blocking on the update. In some of the sort of, I would say primitive database systems, what might happen is if you update a row and then if that transaction is not yet committed and you are trying, in some other transaction is trying to read that from that table, it might just block until the updating transaction decides what it needs to do, whether it's going to commit or abort, because otherwise you might end up returning a row which finally gets aborted. But with MVCC, what happens is the reads never block on updates. Only updates block on updates. So if two transactions are trying to update the same row, then obviously one of the update would wait for the other to finish, but reads don't. But there are challenges. I mean, the updates, the deletes, and the inserts which eventually abort, they create dead versions in your table, and which lead to table bloat. I'm sure a lot of people here would have experienced that. When I started my table, it was just a few gigabyte table, and over the period it went from say 2 gigabyte to 10 gigabyte. And what causes that is the bloat in your table. Every update in to a row also generates a corresponding row in the index. And if you got 10 indexes, that means every time you update one row, 10 new versions of the index rows are being created, or one row in 10 indexes being created. That causes index bloat as well. Now, some of these things might be sort of that's how it used to be. Some of we have fixed partially or fully, but these are the challenges. The MVCC scan that happens on the table has to read every version of the row in the table and decide whether I can see this row or not. And that means a lot of computational resources or even IO resources are spent on that. There are transaction ID wraparound issues. As I mentioned, with newer systems, within months or years, you can basically wrap around your transaction ID. And since the entire MVCC checks are based on transaction identifiers and whether they were committed or aborted, it's important to handle transaction ID wraparound. And we spoke about xmin and xmax attributes in row. They occupy physical storage in your table. So that's an additional overhead so even if your table has say a 4-byte integer, you got a table which is single column, integer column, Postgres would add, I think now we got something like 24-byte row header. So for every 4 byte that you insert into table, you are actually inserting 28 bytes into the table. And 8 bytes of that obviously is because of the transaction identifiers that we store. And then there are other things that we need to store in row headers. So how do we deal with these challenges? The challenge number one, which is the heap bloat or the main table bloat, we have something called vacuum to address that. And vacuum is nothing but going through the table, trying to find which row versions you can safely remove, and somehow sort of reclaim that space from the table. Also, you want to remove the dead pointers from the index as well. And as you would imagine, as the heap is getting bloated, more pages are being sort of allocated by file system for the table. You want to somehow sort of reclaim space consumed by that table. Now, important to note that vacuum, the normal vacuum, it doesn't actually defrag the table. It can only release space free space if it's at the end of the table, and we'll talk about that in a bit. The other challenge was about index bloat, and as I said, we insert new index pointers for every update, and this happens in every index on the table. We solved that partially by something called as heap only tuple, and quite incidentally, I was the person who wrote that feature like 15 years back now, maybe 13 years back. But the idea there was to somehow reduce the number of index updates that you need to do, and we optimize some normal use cases where I mean the bad thing was if you are update before hot, if you are updating a column and you are not even updating an index column, even then a new index pointer was being inserted. With hot, we stopped doing that. So if you are updating index column, then hard luck, you will still have another index pointer. The third challenge that we talked about is MVCC scan has to go through each row and decide whether it's visible or not. And that's not an easy operation because you have to figure out what is the XID of the inserting or committing transaction, xmin or xmax, and then go and look up some other place where basically find out whether that transaction eventually committed or not, and that was sort of a very costly operation. Instead, I think few releases back, maybe 5 years back, we added something called as we started marking pages with a special bit called all visible. So if a page is marked as all visible, the system knows that you don't need to do any further checks for any row in this page, and everything there is visible to everyone. And finally, the XID wraparound problem that we talked about, and that is solved by a special action called as freezing. So when you freeze a row, and you probably would already know there is a vacuum freeze command, right? So when you freeze a row, what you are doing is you are removing all references to real XIDs from the rows in that table and replace them with some special flags and special information so that you don't need to remember about the XIDs themselves, but just know that this row is frozen in a sense that this is visible to everyone, no need to do any further checks. So, to talk more about vacuum, because I want to speak about what has improved there. So vacuum is a 4-stage process. We do a scan of the heap, which is the main table. We collect which rows are now fully dead for every transaction in the system. Then go ahead and scan every index on that table and first remove all the index pointers to those dead rows. Then come back to the heap again scan the entire heap, and then actually remove those dead versions, and then optionally also truncate the heap if it's possible. Now you can imagine if you are doing this on a 4 terabyte table, how long this is going to take. And especially if got say 50 indexes on the table, you have to not only scan the main table twice, you also need to scan the indexes. And even the truncate that happens at the end, the way it is implemented, you have to again scan back and see if no one else has, in the meantime, while vacuum was running, has inserted a row within that range. So you again go back, scan, and then decide to finally truncate. So this is how it works. The first phase is scanning the heap. So I'm collecting the dead tuples, so I'm just marking, so block number 0, tuple 0, block 1. So all dark red boxes are being collected. And then in the second phase, where we sort of clean up the index, we take the list collected in the first phase and then go and check the indexes and find which index pointers are actually pointing to those tuples and remove all those index pointers. I mean, it's for correctness purposes, it's important that the index pointers are removed first before the heap rows are removed. Then we again go back to the main table, we again scan all the, now obviously I'm taking this example with 5 blocks, but this can easily be, 5 billion blocks. So you go to each block, then now go ahead and remove the dark red boxes. You can still touch the dark, the light red boxes, because even though, those are going to be expired at some point, right now there are queries which are interested in those versions. And then finally, you truncate the heap. So because after we removed the dark boxes, the last 2 blocks in the table had nothing left, so you can basically truncate those 2 blocks away. So there are challenges. I mean, I talked about these multiple passes that vacuum has to go through, which leads to excessive I/O, excessive wall generation, which affects your standby operations. The same pages are scanned multiple times. Every time you do vacuum, the same page is going to be scanned, or used to be scanned. I'm going to speak about how that's been solved. So the first challenge about scanning, the same page again and again during every vacuum operation is solved by something called as visibility and freeze map. So what we do in Postgres now, and this has been a big improvement to MVCC, is that we maintain a bitmap 2 bits per page in a separate file. And in that bitmap, what we store is whether a given block in a table requires any vacuum operation. So if all rows in that, for example, in that block were frozen by the previous vacuum operation, we mark that that block as all frozen, and then the subsequent vacuum operation doesn't have to ever scan that block again. Similarly, we store information about whether all rows in a particular block are visible to everyone or not. And if they are, then you don't have to do anything during vacuum operation. You don't have to do any visibility checks for any of the rows in that block. And you can also use index-only scans, which is a completely different topic, but yeah. The few other things that have been added recently to vacuum are now vacuum supports parallel jobs. So what you can do is when you fire vacuum DB command, which generally it will go through a given database and try to vacuum all tables in that database. Now you can say run it with 5 concurrent connections or 10 concurrent connections. So this sort of allows you to make maximum use of resources in the system. We do a lot of good work in terms of the vacuum progress reporting. I remember 5 years back, it was very difficult to know where my vacuum is. I mean, customer used to call us and say, I got this vacuum process running for last 20 hours. I don't know what it's doing. But with the reporting, now we can actually tell which stage of the vacuum processing it's in and how much work it has completed in that. Few more interesting option has been added in PG12 to vacuum, and I want to talk about that because these are newer ones. The first is disable page skipping. We talked about visibility map and freeze map, which are great additions to basically enhance the speed of vacuum. But there are situations, there are times when you don't want to skip any page because let's say your map is corrupt or something has gone wrong and you want to make sure that the entire table is scanned and everything is corrected. So you can say disable page skipping. The default is not to skip any pages, is to skip pages, sorry, based on visibility map and freeze map. But if you say disable page skipping on, then it won't skip any page, and make sure that your entire table is scanned and dealt with. Skip locked is also an interesting. So if you are running it, let's say if you are trying to run a vacuum command on a table, and Simon talked about some of the lock levels in the morning. Typically, vacuum requires share update exclusive lock, which doesn't conflict with reads and writes, but it does conflict with create index concurrently, for example, or it conflicts with access exclusive lock. So what you can do is if you use this option, and if the required lock is not available, which is the shared update exclusive lock, then vacuum would simply skip that table and try and process the next table. In the past, what used to happen is if there is one table, if you're trying to do a vacuum DB of the entire database, and there was one table which was locked by some other transaction in exclusive mode, and it's sort of holding that lock forever, then your vacuum is completely sort of stuck. Now, if you do that, if you say vacuum skip locked, it will, and if the lock is not available, it will say skipping vacuum of the particular table because the lock is not available. This is also a very important addition that has happened in PG12. In PG12, what you can do is you can disable vacuuming of the indexes. So we spoke about how vacuum works. So it scans the table and then it first cleans up the indexes. If you use this option, what you are saying is, I'm not worried about the bloat in the index. What I'm worried about is bloat in the main table, and I'm actually more worried about the entire freeze operation. I want to finish freezing this table as soon as possible. The indexes don't have any transaction identifiers. It doesn't store any MVCC information. That's all in the heap, and that's what I want to freeze as soon as possible. So you can use this option. In fact, at second quadrant for many years we had an extension called anti-freeze, which used to do exactly this, and there were several customers who would find that very useful. But now you had something similar in core, and I would suggest that you look at this sort of seriously. Not do it. I mean, I'm not saying that use this indiscretionally at every time, because that would lead to other problems. But be aware of the new facility. And then finally, there is another option called Truncate, and you can again turn it off or on. And by doing this, you can say, I am not interested in truncating the table at the end of vacuum, because say for example, I know more inserts are going to come and it will eventually again extend. What used to happen is when vacuum is trying to truncate the table, it will grab an access exclusive lock on the table, which will block out all the reads and writes. So we had situations where users would say, I was running vacuum on this table and suddenly I can't read and write from this table for a few minutes. And that's because at the end, vacuum was trying to truncate the table with a strong lock on that table. So if you turn it off, you won't reclaim the space from the table, but you won't have to get a strong lock on the table either. What's coming in PG13 and beyond, this patch I think is already committed vacuum parallel with, till now, vacuum was a single threaded or single process operation. If you now specify the parallel operation, and this is not in PG12, it will come in next release. If you do that, then vacuum can use multiple background processes to now vacuum a single table. Now the thing is, it can't still scan the main table with multiple background processes, but if you got multiple indexes on the table, it can use multiple processes to say scan one index, so you can scan multiple indexes concurrently with the parallel option. So if you have just one index, it doesn't make sense to use the option, but if you got multiple indexes, I would suggest look at this. There is some work being sort of discussed and done on the to resume interrupted vacuum operations, so that if a vacuum fails in between, you can, instead of again starting from the first block in your in the table, you can start from where you left off in the previous operation. And obviously, some developers are working on something called as Heap, which is a completely new storage engine that is being proposed in Postgres, which would alleviate a lot of pain with MVCC, because we are using, say, a different technology to implement what MVCC provides in Postgres. I'm not sure where we are here, but it leverages a lot of good work that has been done. Even like my colleague Alvaro worked on the entire table access method sort of APIs, which are important in implementing pluggable storage that the Heap uses. So these are the things that will come in PG13 and beyond, maybe in few years' time. I think that's all I have. So I hope this has been useful. If there are any questions, I'm happy to answer. Yeah? Okay.
When you are arranging or this indexes, at some point, if you during vacuum, you would be changing indexes, rearranging, and all things like that, right? So at some point, if you decide that okay, I have already reorganized my index a lot, so again after vacuum completed, I'll recreate the index, kind of thing. You have any?
Yeah, I mean, right now in Postgres, we don't do defragmentation in indexes either. So I think, and I could be wrong here, I think there are limited optimizations where if, two index pages are completely empty, then adjacent pages are empty, you can sort of combine them into one. Some limited options are there, but otherwise, we just remove the dead pointers and let the future inserts into index sort of make use of that. But yeah, I mean, in future, maybe it can be done where you rebuild the entire index. That's basically technically challenged because you're also, allowing concurrent read and writes on the table while vacuum is going on.
Thanks.
Any any discussion on changing the 32-bit transaction IDs to 64-bit?
Yeah, I mean, that discussion happens all the time. It's, I think, the problem is.
Any traction?
I think there are a couple of patches being floated, but I'm not sure whether they would find the daylight. I mean, because we already, the complaint is, Postgres row header is already quite large, 24 bytes. If you make it 32 bytes, it's going to be even bigger a challenge. But I think there are opinions are sort of divided on what should be done with that. I think.
The truncate option you said that we need to turn, we have this, but this is already similar to vacuum full, right? The normal vacuum doesn't put any exclusive lock on table.
Well, vacuum full is, it's sort of, it takes an, it rewrites the entire table. So it will block the reads and writes for the entire duration of vacuum.
Right.
Whereas truncate is, you have done most of your job with a low level sort of a lock. Shared update exclusive is not that strong a lock, but only the truncate part, which is the last phase of vacuum, holds the strong lock.
In that part, it will release the last space.
Yeah, it will just, if you turn use that option, that it won't even try to truncate any pages at the end. So
Okay.
it will pretty much not block anything else in the in your database.
Okay, thank you.
Sorry.
Hi. During vacuuming, there are two steps basically. Either you do it in lazy way or eager way. When you're doing it in lazy way, you refer to the visibility map. But if you're doing it in the eager way, you don't go to the visibility map anyways. Now, if you're doing it in the eager way in the first time, and then the auto vacuum kicks in later on, what happens? Who updates the visibility map?
So I don't think there is any. Is there anything called eager? I mean, internally we call it lazy vacuum. But to answer your question, whenever a vacuum happens on a table, which is normal vacuum, visibility maps are updated. If you also do vacuum freeze, then the freeze maps are updated, and those maps would remain intact unless some operation happens in that block. So either you update or delete a row from that block, in which case the visibility map or a freeze map would get invalidated. And then the next vacuum will have to again process those blocks. Does that answer your question? Yeah, we'll speak later, yeah. That's it, I think.
I guess we're done.
Thank you so much. Thank you.
Thank you, Pavan. It was exactly 45 minutes.
Thank you.